planning to add the course that we haven't seen yet checks on it and comes Tuesday for the first time and doesn't find us, she'll know. He or she will know. Okay. All right, we are recording, so let's go to the slideshow from current slide. And let me say again what I was just saying to the class. I forgot that I didn't have Screencast-O-Matic started yet. Tuesday, I'm pretty certain we will not have class because a meeting that I thought we were going to later in the month on the Friday, Saturday has been changed to Monday and Tuesday of next week. So instead of driving to Atlanta, they're flying us to New Orleans. Sounds like a big waste to me, but that's what they're doing. So it's all on the government tab, so I guess they don't care. So just wanted to let you know I'm not going to be here Tuesday, so don't show up for class. We'll try to make that up, and we'll talk about that on Thursday. Say I'll stay late on Thursday and make up the class. We won't have a chance to make up the lab, I don't think, because not enough students will be here, so we'll just make up the class and go from there. Okay. Any questions on anything we've done up till now? All right, where we left off last time.
Test.
Yeah.
Test.
Oh, when will you get it back?
Yeah.
I haven't quite finished grading them all. Well, wait, I did grade them all. But I checked with, just happened to see the registrar in the hall this morning. She held me up, and she was talking about no-shows. And I said, well, how about the people who haven't paid? She said, oh, we need to check on that, yeah. And so I hate to remove from someone from the class to have them show up the next day. And that's why I made the announcement here. Because I still got Jarrell Devontae Collins listed, Lashandria Monique Mims listed, Carrie Michelle Stamps listed. Now, Carrie has started the class before and had to withdraw. So, but as far as I know, none of these are paid, and I assume they're not coming back, but they still have them on the roll. So, since they're still going to let them come into class, I don't want to return your papers and then find out they want to make up the test, and their eyes may land on yours. If you want to see the test, you certainly can. I've got them here. They're all graded. But I was going to wait until I found out for sure if these other people are going to be removed from the roll. Good deal. Thank you. I also have your labs graded too. I don't have them posted on Blackboard yet. This morning I was planning to do that. I had to take care of all the travel for this Phantom meeting that's coming up. Yeah, what were you going to ask? Yeah. Oh, you want to see the test? Okay.
You confused me when you said you had a lab graded.
They are, but you just turned in the lab.
Yeah, that's
Right, okay, right. So I don't have yours graded yet. Okay. I have the two that were turned in. They're graded. So you can see those two, but I can't return them until I get all those in too. And hopefully I'll hear from the registrar sometime. And she said, here's the thing. She said she was waiting on Dr. Crawford to do a letter to the students who haven't paid yet. That's why she hasn't removed them from the roll, to tell them they have until a certain date to pay. He hasn't done the letter yet, and then I found out when I was doing my travel thing, he's already left for New Orleans. So he's not going to do the letter until Wednesday at the earliest. So I don't know when it'll be done. But I'll try to get it to you, but certainly you can come look at your test. But I just can't return them until I find out if these other people are for sure not going to show up. Good deal. Any other questions? Sorry I can't do it now, but I'm just afraid. I've had that happen before. Someone says, oh, well, I've been sick, and yeah, I would have been here, but yeah, and then they have to catch everything up. So let me make sure they're going to remove them from the roll before we do that. Any other questions? Good question, though. All right. Now, I have up here Jupiter, but I think if you recall, we had gotten through Mars but I didn't notice these examples. Some of these may be worth just a peek. I'm not going to do them in detail. It says, if the noontime surface of Mars can reach as high as 20 degrees Celsius, does anyone know how much that is? 20 degrees Celsius. 68 degrees. It's just about room temperature. Okay, we're at 71, I think, so we're a little above this. Is that warmer or colder than your typical room temperature of 72 degrees Fahrenheit? Using equation 4.2. Well, 4.2 was in a chapter we haven't had, okay? So you can go back and do it, and they did the Fahrenheit to Celsius conversion and got 22 degrees, okay? If they had done the Celsius to Fahrenheit, they would have found 68. So no, it's not, it's colder. Cooler, not very much colder, okay? Only slightly higher than the warmest summer daytime surface temperature on Mars. So normal room temperature is as warm as it gets, okay, on Mars at noon in the summer. Okay, Mars' coldest temperature are around 140 degrees, minus 140 degrees Celsius. What temperature is that in Fahrenheit? And since we haven't done temperature conversions, I won't make you do that. If you want to see how to do it, it's really a simple formula. Would you want to see that, or you want me to just tell you? You want to see it, okay? Pretty simple formula. Yeah, you got it. Okay, let me get my pen activated for dark. Okay. And they gave you Celsius, so to get degrees Fahrenheit, that's equal to, that's a ratio. You multiply that by degrees Celsius. So what do you need to do? You have to have your ratio down here, degrees Celsius to degrees Fahrenheit, just like we did before, so these will cancel out. Our degrees Celsius, I should have written that in. I'm not thinking too well here. There we go, I'm going to write that in. That's negative 140 degrees Celsius. Okay, so we want to cancel that out. So, what is the ratio of Celsius to Fahrenheit? You are saying it. Okay, 5/9 or 9 to 5. One of those two ratios. Well, a Fahrenheit degree is smaller than a Celsius degree, and here's how you can remember that. What is the freezing point of water Fahrenheit? 32. What is the boiling point of water Fahrenheit? 212. What's the difference between those? 180 degrees. Okay? What's the freezing point Celsius? 0. What's the boiling point Celsius? 100. What's the difference there? 100. So 180 to 100 is 18 to 10, which is 9 to 5. So 9 degrees Fahrenheit corresponds to 5 degrees Celsius. And since we want Celsius on the bottom, we put the 5s down here and the 9 up here. When you're going the other way, it's 5 9s. Okay? Now, that gets you up to 0 Celsius. Okay? So then you have to add 32 degrees Fahrenheit to that, because the 0 Celsius is freezing point. You have to add to this. So, let's just divide the 5 into 140, and that would go 28 minus 28. 9 times minus 28 is 72. 1825 minus that plus 32 is going to be, that goes away, this will be a 2, negative 220 degrees Fahrenheit. I don't think I want to be there then, okay? I don't want to be on Mars in dead winter, okay? That's the Mars cold, that's Mars coldest temperature is around minus 140 degrees Celsius. That would be about minus 228 Fahrenheit. Okay, so you see, in the summertime, if there was water in the form of ice on Mars' surface, it could melt because it gets up to room temperature. Okay, but it's not going to stay melted long. It'll refreeze pretty soon. There is another example given. How fast would a rock falling from a 60-meter high cliff on Mars be traveling when it hit the Martian surface if the G for Mars, that's the acceleration due to gravity for Mars, is 3.8 meters per second squared. Do you happen to know what G is here on the Earth? 9.8 meters per second squared. So this is close to a third. Okay? How fast would it be? Again, you need the formulas you got early in the book, which you haven't done, so I'm going to leave that alone. It'll be about 21 meters per second. Now that may not mean a lot to you, not moving all that fast. But 60 meters high is pretty high. On the Earth, that would be moving much, much, much faster. Okay? Now, example 15.8, how long did it take the falling rock in example 15.7 to hit the ground? On Mars, it would be 5.6 seconds. Here on Earth, a lot less than that. 60 meters is pretty far up there, but it would be because the acceleration is much greater. Okay. Now, just thought maybe since they had them here, but all of them, that's why I said, most of these examples depend on stuff that was in the first half of the book, which y'all haven't had. So I don't expect you to be able to do all those. But when they're interesting like that, I thought it might be worthwhile. Okay, let's move to Jupiter. Now, where have we had to go from Mars to get to Jupiter? Okay? Pretty rough trip because you had to go through the asteroid belts. But even though it looks like there's a lot of asteroids out there, and there are, it's really, space is so big, you probably could get there and hardly see any asteroids yet because they're so far apart from each other. How far would you have to go? Sun to Earth is 1 astronomical unit. Earth to Mars is another half an astronomical unit. Then to get from there to Jupiter, 3.5 more astronomical units. More than twice as far as Sun to Mars before you get to Jupiter. Well more than twice. Okay? In fact, 3 times. Okay? More than 3 times. Okay. So, it's way out there. And we aren't even near the end of the solar system. It is by far the most massive planet. 318 times the mass of Earth. Wow. 318 times more massive than we are. And we're really dense. Remember, we're the densest planet, so it is huge. It's mostly hydrogen and helium. Where else do we see hydrogen and helium? On the stars, the sun. Yes, those are the main gases on the sun. And so the idea is probably in the sun's formation when it was blowing up and doing all sorts of stuff before it settled in to be a star, probably blew the hydrogen and helium, some of it way out there, because the next 4 planets are mostly hydrogen and helium. But it does have an iron silicate core. Guess what kind of core we have? Mostly iron. Guess what most of our surface is? Silicates. So, it does have some of the same matter that we have, but that's in the core. So down in the core, there's a fair chance that it's solid. But that core is so far down with so much pressure, with that much mass over it, it could be a solid liquid. I don't know. I don't know if they know. But they do have an iron silicate core. This is a picture of it. Cutaway view of Jupiter. Here is your iron silicate core. Now just the core is 10 to 15 Earth masses. So you could fit 10 to 15 Earths just in the core of Jupiter. And it's a pretty small core. Outside of that, we have liquid metallic hydrogen. That's a weird sounding combination, okay? Now, why would you say liquid metallic hydrogen? Well, a metal has pretty much good conductor of electricity, so evidently this hydrogen goes together in some, not quite a crystal structure, but they must share electrons, and electrons flow and hold them together. Because hydrogen is just a single proton and a single electron, okay? That's all there is, but they must go together and have some metallic properties and some liquid, of course, properties, okay? But wait a minute. To make hydrogen liquid, you have to get awfully cold. So maybe this core is not as hot as I was saying it is, because that might be an awfully cold place where you left liquid metallic hydrogen. Then, near the surface, that is liquid hydrogen, not metallic anymore. And by the way, look at these distances. This is about 35,000 kilometers in. That would be approximately 20,000 miles. Huge, okay? And then liquid hydrogen here, about 20,000 kilometers. That would be about 12,000 miles. Okay. And then the atmosphere, again, like I said, mostly hydrogen, helium, some ammonia clouds, and that's about 500 kilometers thick. Okay? So the surface, when you really do get to a surface, is liquid hydrogen, which is very, very, very cold. Okay? And above that is an atmosphere of gaseous hydrogen, helium, and ammonia. Now, the other reason this is liquid is because of the pressure. The gravitational pressure pulls it so tightly that it becomes liquid there. So it may be at warmer temperatures than what we're used to seeing hydrogen. But when you pressurize, you can force the molecules closer together. Okay. Here is an actual picture of Jupiter. And this is a very famous feature of Jupiter, is the Great Red Spot, is what it's called. Okay? And I think they do a little bit in the book on that. Oh, boy. I just caught my eye on this. Back on the same page as Mars, a case study. Did we talk about this? Is it worth the cost for space travel? It's really expensive stuff. Is it worth the cost? A lot of people may argue on that. This is top of page 386. But man, we have, number one, learned so much, and number two, developed so much. Yeah.
This might be a stupid question, but how did they come to the conclusion that it has an iron silicate?
Okay. Good question. Just about every solid in the solar system basically has iron in its core. So that's one contributor, okay? The asteroids, the comets, most of them have iron or silicates as most of the structure. So it's a pretty good guess, okay? Iron, remember, when you have these fusions going on, iron is kind of the end product. So iron is out there in lots of places. Now, we can measure the diameter of Jupiter, okay? So we know how big it is. And there's things called mass spectrometry. I don't know if that's exactly what they use, but I wouldn't be at all surprised if it isn't. Something like that anyway. And they can come, well, and then too, by the gravitational field, we know its mass. because mass is related to gravity. Gravity is related to mass. So we know its diameter and we know its mass. Okay? Approximately, anyway. Well, then they start calculations. They know the surface, or the atmosphere, is hydrogen and helium. Pretty light stuff. And they probably, I'm just guessing here, have set probes down and maybe crashed into the surface and taken measurements and know the other stuff on the outer part, very outer part. Okay? Now, to get the mass and the volume to work, they have to come up with the density of the planet, knowing it gets denser as you go down. And by the time you get there, the only way it can be, and knowing that the most predominant elements in the solar system are iron, is a very good, reasoned, supported, educated guess. Now, that's my guess. Okay, they may have some better ways of doing it. I don't know, but they do a lot of inferences like that. They know the volume. They have a great estimate of the mass because of the gravitational attraction. So they know, and they know what the outer constituents are. They have to calculate what could be in the middle, and there's no way around. It has to be a pretty dense material and fits all the characteristics of iron. Everything else has iron in it, so I think it's a pretty good guess. That may be a good paper topic. So hang on to that. That might be worth researching. All right. Yes, a much better picture in our text of the great red spot. Only in our text, it looks like a great yellow spot. Okay, this is on page 388. The same picture we see here, or almost the same, it's twisted a little bit. What looks red here looks yellow there, and that's probably just the way they did the color schemes on it. But it's actually called the Great Red Spot. And what it is, let's see what it says here. The spinning Great Red Spot. Now this is basically how Galileo and others knew that Jupiter had to be rotating. They saw that red spot moving. Okay, maybe not in one night, but night after night it had moved. So they knew it had to be spinning, rotating. So I imagine they could actually see the motion themselves because it's dominant enough that you can see that. So it's called the spinning Great Red Spot, as observed by the Hubble Space Telescope. In general, Jupiter's dark features are warmer and the light features are colder. The Great Red Spot soars about 25 kilometers, that's 15 miles above the surrounding clouds, and is the coldest place on the planet. Now, they just said the dark features are warmer, light features colder. Why do they call it the Great Red Spot well, I don't know. It looks red, so it seems like to me these would be colder areas there, but they say that is the cold spot. Okay? And it's a storm. It's a swirling storm that's been going on as long as we've looked at Jupiter. So their storms last a while, okay? And the latest I've heard on it is it does seem to be diminishing slightly. So maybe in a few years or decades or centuries, it may not have the Great Red Spot anymore. Maybe a little red spot or no red spot at all. Okay. Now, again, our text, this is one thing about this edition over the previous ones, it has a lot better shots in it. Like the Jupiter shot, that's from Hubble, that's a really good shot there. Okay? Here are and we're going to get to these, so I won't say it yet. Okay. Now, for some reason, whatever slide was supposed to be here isn't showing up. But what else about Jupiter? As I just indicated, it has a dynamic atmosphere. It's not just hanging there. It's not just spinning with the planet. It is moving. And the atmosphere is made up mostly, as we said before, hydrogen, helium, sun-type elements, and ammonia. Now, ammonia really and methane too. When I think ammonia, I think amines, which make up amino acids, which make up proteins. Okay? Those are all related. That's what the AMM here stands for. NH, ammonia is NH3, and amines are NH4 with other things on them, and amino acids all have nitrogen in them in some sort of NH configuration. So when I think ammonia, I think it came from something living. Obviously not, okay? In fact, this is, I guess, probably where most of the nitrogen is in Jupiter, is in that ammonia. So that ammonia source is very different from the Earth. What do you think of when you think of methane? It's probably not the best thing to think of methane, but it's a greenhouse gas, I'll go that far, okay? And it's also a gas that's given off in flatulence, okay? Cattle produce an awful lot of methane. This one would be surprising to you. Termites. You eat wood, they give off a lot of methane. That contributes to greenhouse gas. Those are fairly natural occurring greenhouse gases, so you have to have them. But when I think of both of these, especially methane, I think fossil fuels type thing, okay? But there's no fossils there. There's no living stuff there. This methane came from another source. Carbon, though, we know that when helium fuses, in the step after hydrogen fusion to helium, helium fuses to carbon, carbon reacts with hydrogen, that gives you methane. So methane there is not, it's the same as methane here, but it's just not from the same source. And then, surprise, surprise, there is water in the atmosphere there too. Probably ice crystal water because it's pretty cold, and there are other things in the atmosphere too. The Great Red Spot, we've already talked about, a huge, enormous storm on the surface of Jupiter, very active, seems to be diminishing a little bit. Now, at least I've heard that. Now, it says a large system of varying satellites. Now, let me explain to you sort of how large. Oh, okay, number one. It has the most number of moons of any planet, by far. I don't even know their latest estimate. Don't think the book, I know the earlier editions didn't give an exact number, and I don't see one here. Have you seen it? There are, how many? Tens, yeah. I'm guessing it's close to 50. It may not be. 30 to 50 would be my guess. So tens of moons. Okay? So that's what they mean by a large system of varying satellites, meaning moons. But not only that, we haven't gotten there yet, but you know this already. What is Saturn famous for? The rings. Well, actually, all of the giant gas giants have rings. They're just, most of them not as predominant and dominant as Saturn. Saturns are just out there and beautiful. The others have rings, but they're very small, pretty much insignificant. Okay? But that's also things floating around out there. Okay? But mostly here they're talking about the moons. The four biggies. Oh no, okay. Now, this is so confusing to me. In the old text, which is where this came from, and if you look back, well, it's just really confusing. On page 388, that great Hubble shot that they have there, this is the storm. Okay. To me, this was the Great Red Spot. It's red. But when the feature here is looking at that one, okay? And I think, wait a minute, what are you talking about here? Now, we don't have that figure in our text. Ours is the Hubble one. But when I look at that, then I think they're talking about, and when it says the coldest place on the planet, I'm guessing they're talking about this thing near the Great Red Spot. But they've never described that very well. And why do they focus on this if that is indeed the Great Red Spot, which is red, it looks like it. But then this, I could easily believe you have one huge storm here, and it's created another storm here. You know, if you look at the weather map sometimes, you have high pressure here and low pressure pretty close to it. Not real close, but fairly. I'm guessing it's almost like that kind of thing. Where that may be the cold one, and the Great Red Spot is maybe a bit warmer. I don't know. That's my guess. What do I know? Here are another picture of the four, they call them the Galilean moons. Now, why do they call them that? Named after Jesus' home country, Galilee? No, that's not why. Ah, you got it. Remember, he's the one who found out about the telescope that someone else in Northern Europe had invented. He was intrigued by it. He read a little bit about it and started making his own. And he made enormous improvements when he made his prototype of the telescope. And then he looked out there at some of the things in the sky, and that's when he saw Jupiter, which is one of the brightest things out there on certain nights. And when he started studying Jupiter, he saw that red spot, saw it spun. Wow, it rotates, maybe we rotate. That supports Copernicus' idea. But also, his telescope was good enough to be able to detect these four largest moons of Jupiter. Like I said, it has tens of moons, 30, 40, something like that. However many it has, these are the four big ones, so he could see and detect these. I think this is the same order they are in ours. The four Galilean moons pictured by NASA's Galileo spacecraft, named after Galileo, okay? And they're the Galilean moons, okay? While they were orbiting Jupiter, from left to right, they are Europa, is on top left here. It's the first one in your book. Ganymede, which is the smallest of the four. Callisto, which is the largest of the four. I'm sorry, I got off. Left to right. Io is the first one. The first one is Io. Then Europa is the smallest. Ganymede the largest, and Callisto the last one. Wait a minute, yeah. Okay. Yeah, Callisto the last one. Then they have a period. I thought it was a comma, and they mentioned Io again. Io and Europa, the first two, are about the size of Earth's moon. I'm guessing Io is a little larger, Europa is a little smaller. Ganymede and Callisto are slightly larger than Mercury is, the smallest planet. Now, if Pluto was included, it's going to be really tiny. All these would be bigger than Pluto. So, our moon is somewhere in between these two in size, and these two are actually larger than Mercury. Okay? Wow. Now, is that a little bit surprising to you? Remember, the Earth is one of the four little planets. Compared to these gas giants, 316 Earths go inside Jupiter. Okay? How many was it? 15 Earths go inside the core of Jupiter. Okay? Jupiter is huge. And yet their largest moons, their four largest moons, are in the same ballpark as the size of our moon. And we're such a tiny little planet. We have another biggie for Earth, not that biggie, but size ratio of Earth to Moon, or let's say it the other way, Moon to Earth, the largest size ratio of any satellite to any other planet. no one comes close to having a moon relative to our size as large as our moon is. It's pretty incredible. Okay? What is the other feature that we are the largest in? Density. We're the densest of the planets. Very good. All right. Now, your book has something that our book doesn't. Okay? It's going to show these later, but it's in a different section. But this is the picture of Jupiter in ultraviolet. And again, this is taken from the Hubble Space Telescope, the Wide Field Planetary Camera 2, whatever that is. And this shows the ultraviolet radiation on Jupiter. A pretty impressive picture with some captions there that they don't describe. So I can't really tell you all of what they're doing, except I think they're talking about this former comet that got just a little too close to Jupiter, and Jupiter is so massive it pulled it out of the comet's orbit, and the comet crashed into the surface of Jupiter. And that's what those pictures are showing. We'll see it on the slide set when we get to the comets. Not seeing them yet. The other thing, where is Jupiter in the solar system? Give me an idea. Sun's here, then Mercury, Venus, Earth, Mars, asteroid belt, exactly. Then Jupiter, just outside the asteroid belt. Okay, now get this, folks. Here we have this big, incredibly massive planet. So much bigger than, I would almost say, all the rest of the planets put together, maybe close to it, maybe not quite. Just outside the asteroid belt. Now, two things could have happened. They're going to talk about one later, so I'm going to save that. But I'll mention this one now. Jupiter also has the largest number of moons, satellites. In my mind, it reached out there and grabbed a few asteroids. It's big enough to do that. The gravitational field of Jupiter is huge, and I wouldn't be at all surprised if some of those moons that used to be asteroids, Jupiter pulled them away. That's just my speculation. All right, 389, example 15.9. Assume that one of Jupiter's moons receives its peak solar energy over a 10-hour period. Okay. How much energy is heating 1 square meter of the surface of Jupiter's moon during that peak time? Okay. Now they use the solar energy in that table 15.1, which had all those planets listed. Okay. And that's, multiply that by the duration of time. Jupiter was, very last thing there, 0.08, and you're going to and by the way, the 0.08, they don't give the units, do they? Yes, they do. Calories per centimeter squared per second, okay? And what you have to do is multiply that area and the duration of time it's received. So 10 hours, and they really do a bad job of this. Well, on this page they do. The next page they must pick up and go, yeah. You have to multiply the 10 hours by 3,600 seconds per hour, 3600 seconds per hour to get seconds. You also multiply 1 square meter by 10 to the 4th square centimeters. So basically in that 10-hour period they received about 2.9 times 10 to the 7th calories. Again, a lot of that is unit conversions and things like this, which we haven't done that much, but if you find that interesting stuff to do, which I do, you might want to take a look at that. There's another example there. An interesting question exists with regard to whether liquid water could exist on Europa. Europa being the moon just a little bit smaller probably than our moon. Okay? One of Jupiter's moons composed of water ice. Consider that a 20 centimeter thick area of ice with a surface area of 3.5 times 10 to the 6 square centimeters exist on the surface of Jupiter's moon. Assume that they go on to all these assumptions. So if you want to read that, go for it. All right. Any questions about Jupiter? Largest planet, largest mass, largest diameter, most number of satellites or moons. So let's move on to Saturn. Now, how far it was from the Sun to Jupiter? About 5 astronomical units. How about Sun to Saturn? Almost twice as far. So here we have Mercury, Venus, Earth, Mars, asteroid belt, Jupiter, and then almost that distance again before you reach Saturn. I mean, you can fit everything else that's in here between. It's amazing the distances here. 9.5 astronomical units. That's almost twice as far from the Sun as Jupiter, which is its closest neighbor. It has these rings of particles. Now, they're small particles, dust, icy, whatever, and they reflect light, and that's what makes these beautiful, beautiful rings. The density, less than the density of water. So, if you had a big enough pool of water, Saturn would float. That's unbelievable. That planet is less dense than water. The surface is very similar to Jupiter. Okay? Liquid, hydrogen, below, all that kind of stuff. Now, before I said, and I thought I was right on that, Jupiter, I think, is on the order of 40 to 50, because Saturn, they say, has 30 satellites. Okay? The largest of these is Titan. That means big, by the way, okay? And that is the only moon we know of with a substantial atmosphere. Now, they don't say what the atmosphere is made of, but that's pretty interesting. None of the other moons that we know of have much of an atmosphere, but Titan has a substantial atmosphere, which is more than you can say for Mercury. It has almost no atmosphere. More you can say for our moon, it has almost no atmosphere. And more than you can say probably for Mars. Mars has an atmosphere, but I would no means call it substantial. So Titan's a pretty big deal, and I think I've heard this somewhere before, that it is actually larger than Ganymede, which was, I think, the largest one on Jupiter. So it's a good sized moon. So it would make it larger than Mercury if that's the case too. Okay. All right. This is a picture, I think, taken by the Huygens. There was some other name, Calypso Huygens or something like that. It was a European Space Agency craft that really stayed around Saturn a long time. I wouldn't be surprised if these pictures of these rings aren't from that. Whatever, they're really beautiful. Okay, again, dusty, icy particles that float around Saturn. That's all they put here on Saturn. I know that, oh, and by the way, go back to Titan. Cassini-Huygens, I couldn't remember what the first one was. Cassini-Huygens mission entered orbit around Saturn on July 1st, 2004, after a 3.5 billion kilometer, that's 2.2 million mile voyage, 7-year voyage from the Earth. That's to get from Earth past Mars, past the asteroid belt, and past Jupiter. That little bit of our solar system took 7 years to do. Okay? Establishing orbit was the first step in a 4-year study of Saturn and its rings and moons. Cassini has observed that Saturn's largest moon, Titan, has a surface shaped by rock fracturing, winds, and erosion. Among the new discovery is a 1,500 kilometer or 930 mile long river, not of water though, liquid methane. Now, methane is one of the lightest of the organic gases, CH4. That's all it is. 1 carbon and 4 hydrogen. That's a very light. It's on the order of the same mass of water vapor. Okay, so very, very light. So it is hard to get into liquid form. It has to be awfully, awfully cold. Saturn is. So it has a liquid river of methane. Don't think we could live there, okay? Titan's atmosphere is rich and organic. Now, when I read organic today, and when we do it in later chapters, we're going to mean having to do with life forms. That's what the word organic supposedly means. Once an organism, basically. When they're saying organic, it means carbon-based. That's all. Never was a life form that we know. That carbon that was fused from helium. That's the basis for that. Okay, so when it says organic, now we don't mean coming from living material, but that, meaning carbon-containing molecules. Most of the clouds on Titan occur over the south pole. Scientists believe that is where a cycle of methane, rain, runoff, and channel carving, liquid methane evaporation is most active. Okay. This is another pretty picture, and this was not in the earlier editions. That's why I'm taking some time to look at it. They're naming the rings. Okay. They mention a D ring that I can't even see. Then a C ring, I think I'm beginning to see a little bit. B ring is pretty obvious. I think that's the one we usually see. An A ring that we see. Usually, I had throat and everything is clogging up. Janus Epimetheus, okay? Never run into that before, okay? That, I guess, is a ring that I can barely see. And then they have Cassini's Saturn Orbit Insertion Ring Plane Crossing, okay? What a mouthful that is. I don't think that's a ring, that's just where they went through the rings. And then there's Mimas Enceladus or something like that, which is a little easier to see. Tethys or Tethys and Dione, and then finally Rhea. I can barely make out those last three. In fact, I'm hard pressed to say. I had to read to see what these words are here. I thought they can't be the moons. No, they're outer rings. Okay. So that, I think, wraps up pretty much what we have. This book does a lot more on Cassini because we got the data and they analyzed it since the last edition. I would definitely read that. One of the shows that he does, if we get to go through the planetarium, is on the Cassini-Huygens mission, and he takes you through it in really interesting detail. Okay? And then we get to Uranus and Neptune, and guess what? They don't even give them a section of their own. They're twins out there, okay? Except separated at birth, a long way apart. Remember where Saturn was? How far out? 9.5 astronomical units. What happens if you double that? 19. Look at that. So we had Mercury, Venus, Earth, Mars, asteroid belt, Jupiter, Saturn, and then that's Uranus. Okay, way out there. And then Neptune, not quite twice, but still almost at the end of the board out there. I mean, amazingly far. These are the outermost gas giants, okay, giant planets, very similar to each other, especially in their internal structure. If you look at the data on the table 15.1, you'll see many of the characteristics, their radii, their masses, their constituent, what they're made up of. All these things are so very similar. They really do almost seem like twins, except for this. Now there's Neptune. We don't have the picture they do in the book of Uranus. Now, I was ready for a question a lot like what Ricky was asking earlier. How do they know this? When I heard that Uranus orbit, axis of rotation was nearly horizontal, how do you know? Have we gotten close enough to see? What is there to see? I don't even think the most powerful telescopes you can tell about its rotation. But if you look at the picture there, you'll see how we know. Notice the ring. Now I said all these gas giants have rings. Uranus has one that is somewhat visible, especially in that shot. And whereas Saturn's rings, there's a little tilt to Saturn's axis, but the rings are pretty close to horizontal compared to the sun's ecliptic, right? Look at Uranus. That's how they know the axis is almost horizontal relative to the sun, because of that ring. The ring has to be going around the collar. No, that's something else. Around the axis. So therefore, if it's up like this, the axis must be spinning close to horizontal. Okay? Whereas Saturn, did they show the picture of it? They really didn't. But you saw other pictures. It's nearly, the rings are almost horizontal, not vertical. Okay? See if there's anything else here. There are a couple questions, and I don't think they'll be, let's see. The sun's brightness at Earth's distance is 1 times 10 to the third watts per meter squared. That's 1,000 watts per meter squared. Using the inverse square relationships, how bright is the sun at Saturn? 10 times further away from the sun than is the Earth. Well, the inverse square relationship said that would be 1 over 10 squared, so that would be like 1/100th of the brightness as on Earth, so that would be about 10 watts per meter, and that sure enough is what we got. Which planet would experience the sun's brightness at only about 1/400th of what is observed on the Earth? Well, if Saturn is 1/10, it's got to be Uranus or Neptune, and it happens to be Uranus. Okay. Any questions on Uranus, Neptune? And by the way, if I'm not mistaken, we have had a probe, probably since this book was written, that we've been getting data from since on Neptune as well. So we probably know more now than what is written in the book. So any of these that there's fairly recent stuff on, that could be more paper topics if you're interested. Now let's look at some of the smaller bodies in the solar system. Okay? 3 general classifications of these. Comets, asteroids, and I don't like that they call them meteorites. They should say meteoroids. And you'll see later why I object to them calling them meteorites. That should be meteoroids. They're out there, just floating around in our atmosphere. Small bodies. These are left over from the planetary and solar and planetary formation. Remember, for the Earth to become a star, it went through fusion, blowing things out, reaching equilibrium. I mean, stuff was probably flying all over the place. And some of this junk just got thrown out there. Never came back. But it's still there, hanging around. Now, mass of the smaller bodies may be 2/3 of the total solar system mass. Anything strike you wrong with that statement? I think I said when we started the chapter, the very first page of the chapter, I thought it was the first page. Yeah, first page. The last paragraph on page 369, what's the first sentence in that paragraph? No. Page 379. Oh, yeah. You're back in the previous chapter. Moons and minor members of the solar system added together. So, by that statement and this statement, they can't possibly both be true. So what they mean is, the mass of the smaller bodies may be 2/3 of the total solar system mass, except for the sun, because the sun is 700 times all of it put together. So that could be, so 2/3 of the mass, except for the sun. Take the sun out of the picture. Jupiter, Saturn, Uranus, Neptune, the asteroid, well, no, asteroids are part of it. Earth's, Mars, Venus, and Mercury, and their moons. Notice they don't include the moons here as smaller bodies. They are smaller bodies, but they are associated with the planets. So take those out, those big, massive objects, those are 1/2 as much as all the rest of it put together, except for the sun. Okay? Now, what are some of these smaller bodies known for? Well, they hit some of the larger bodies. Okay? And this is the thing they were looking at back on when we were doing Jupiter. Comet Schumacher-Levy got a little too close to Jupiter, and Jupiter pulled it apart. And the fragments, 9 larger fragments, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 1. I don't know which they. There's a bunch of fragments. 9 bigger fragments are shown here. Now, I don't know if you can see them here. I have trouble seeing them here. I think this may be this right here, or this here, somewhere here. They're seen. Now, guess what famous astronomer discovered this? Not. It was a guy looking out of the telescope in his backyard, an amateur astronomer, just someone who liked to stargaze. He had it set up back there. He thought, let's look at Jupiter. He said, what is that line of speckles there? What is that? So next morning, or maybe that night, he emailed or contacted or somehow got in touch with the people he knew that were professionals and said, I saw something on Jupiter. I can't figure out. Never seen it before. And they started looking, and they said, look at that. And they started tracking back and said, whew, maybe that used to be Comet Schumacher-Levy. We had lost it. There's where we lost it. So it was discovered by an amateur, just someone who liked to stargaze. And there are lots of them out there who like to stargaze. Okay? So this is when we know these smaller bodies when they hit something else. Okay? We knew about Comet Schumacher-Levy. I mean, obviously we did. Named after two people who discovered it probably about the same time. Probably have been around quite a while. We've been tracking it for a while, and that's why we knew it was near it. We couldn't see it anymore, so they say, yep, that must be it. So let's look at the first of that group, comets. Now, comets exist in two general locations. They have weird names. The outermost ones are called in the Oort cloud. Now, I don't know what nationality Oort came from. I'm guessing something like Danish or Netherlands or somewhere like that. I don't know who that's named after. It'd be a good paper topic, by the way. But these are comets of long period comets, greater than 200 years. Now, what does that mean? From the time they leave the Oort cloud somewhere way out there and come in and get fairly close to the sun and swing back around and go back out where they were again, that trip takes about 200 years. So you'll never see one of these twice in your life, okay, unless you're going to live an awful long time. Okay, you don't usually see them anyway. But that's what they are, really long, short period, long period comets. Where do they originate? 30 astronomical units to a light year. A light year away. That's pretty far out there to still be considered our solar system. It shows our sun is really massive to hold something in 1 light year away. Okay? So basically, it's from Neptune's orbit out as far as the sun has any influence. Okay, that's the Oort cloud. Now, they don't mention it here, but I think there's going to be a figure, and I'll wait to say that. The other place that they originate is, and I've heard it called several things. I think the right pronunciation is Kuiper Belt. I've heard someone call it a Kuiper, which could be some. In fact, most languages, an I doesn't have a long I sound, it has a sort of a short E sound. So that may be closer to it, but I've heard it most of the time called Kuiper Belt. Now, I actually heard the lady at the Birmingham Southern called it the Jupiter Belt. What? Because I thought I was mispronouncing it because I didn't remember a T in it. Now, as soon as we left the planetarium, I didn't even drive away. I got my book out and started looking it up and thought, no, she was mispronouncing because I thought I was. So I think it's pronounced usually the Kuiper Belt or the Kuiper Belt. Okay? The origin here is comets that are less than 200 years in their orbit. Now, when I say orbit, that's not a circular orbit. Highly elliptical. It's really close to the sun and then goes way, 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 way far away. Now, the Oort cloud, this is what I was going to say before, is a cloud. It's just out there. The Kuiper Belt, it's a belt. It's a disc-shaped region, and this is from 30 to 100 AUs from the sun. Okay, look at this. Oort cloud comes in as far as 30, and this is as close as 30, okay? So this only goes 100 AUs. It doesn't go nearly to a light year. But you see, this is the belt. It's a disc-shaped belt, and the Oort cloud is just a cloud. So some of these are about the same distance away, but most of these are farther. Most of these are on the near side. Okay? The gravitational nudges deflect objects toward the Earth. I don't know for sure what they mean by a gravitational nudge. Here's my guess. This is just a guess. Stuff that's way out there kind of just floats around and does its own thing. It's not following certain orbits or other things like this. It just does. And every now and then, it might get close enough to another something out there so it starts feeling the gravitational pull. And if that gravitational pull moves it toward the sun, and it doesn't have anything to take it around, that's what launches it slowly toward the sun, but then the closer the sun gets, the faster it goes, and then it starts losing speed and it goes back out. So that's my guess of a gravitational nudge. Something messes with it. Gets close enough that pulls it, pushes it, not pushes, but pulls it. Now let's take a look. This is almost the picture we have in our text. Not quite, but it shows the scale of the solar system. When I think solar system, I think the sun and those planets and their moons and the asteroids, right? Okay. Everything I just described is right there. Okay. The sun in the middle. This is a blow up of this right here. Sun in the middle, and then this is the orbit of Uranus. They don't even show the intervals. This is Neptune. Now remember what I said about Pluto? Out of sync with the others. These are all in sort of a plane. That's way out. I have a name for it. I can't think what it's called. Angle of inclination is terrible. The elliptical orbit is bad. So that's why it's not really a planet. The other planets are all in the disk. It's wacko to the disk. Okay? So all this, Pluto and beyond, okay? Neptune, Pluto, and beyond, it's all in that little space right there. Okay? Beyond Neptune and Pluto, that's where okay, now this is where the one in the book does a better example than here. Okay? This is the Kuiper belt. You see, there's more of them closer. They go from Neptune, 30, and Pluto, beyond 30 astronomical units out to about 100 or so. And they all are pretty much accumulated in this disk. Goes around there. I mean, some of them could, I don't know how far, 100 astronomical. Well, this is 50,000 astronomical units. So 100th of that would be 100 astronomical units. Okay. These are not making tremendous sense here, but I guess we're okay. Then this is the Oort cloud. Not in the belt, but just out there. Some of these are also as close as 30 astronomical units, but they go out to a light year away. Okay? And the center of our galaxy is that way, from here. You can't get there from here. Now your text, this new edition, has a little bit, they show the Oort clouds for what it is, and then the Kuiper belt, they blow up that center bright area there and show that is the Kuiper belt. That's how I'm pronouncing it anyway. And then the little dot that's in the middle, that's our whole solar system. The rest of us, the 8 or 9 planet, dwarf planets and stuff, it's pretty amazing. Okay. So that's what a comet is. And that's where comets live or come from. Okay. Before we go there, let's just look at the table 15.4. These are examples of spacecraft missions to study the comets and asteroids. And frankly, I hate that they just put those together as if they're related somehow. They're not. They're really different from one another. But, and basically the comets we've studied are those that have come in from way out there. We study them when they're in here, We don't study them out there. We don't live long enough to study them out there. They are the ones that come close. So in that sense, they're more, I guess, like asteroids.
Did you see that they landed?
Yes. Boy, which one of them was that?
But it was already making a sound. They played. Did you hear the sound that that comet was making?
No, I don't think so.
They had like a signal. It was like,
And it wasn't our radar or something. It was it coming from there.
coming from the dam.
Interesting. Interesting.
Yeah, but they landed it on there. They lost contact with it for a couple of hours or something.
Right.
They said it came back up.
Yeah.
I haven't heard anything else about it.
One of the last visits we made to Sanford, he had a thing on that, and he called, I can't even remember the name of the comet, but he calls it the rubber ducky, because that's what it sort of looks like. Almost has a duck's head and a round thing, looks like it could be almost, not quite, a toy that you could play in a pool with, a kid could. And what happened, I think it was European Space Agency, and I want to say it was Cassini-Huygens, but it probably wasn't. It was one of the others, I think. And what they did, they went to land on it, and they really didn't do a great job of calculating well. What happened, when they landed on it with such force, they bounced, because it had almost no gravity, and it was like a collision, boom, and it bounced way up. And then they had to do it all over again and come in much more slowly and do. And I think the bounce shook up their communications and stuff, and they were afraid they had lost it. But then they, like you said, it came back and they did it. And they did, I think, finally get to land on the surface and take some numbers. And that's the first time anyone's ever done that.
If I remember it correctly, they launched it like 2 years ago.
Oh, yeah, it was.
They circled the Earth to build up speed. They went
Right.
around the Earth to build up speed.
Yeah.
And they got to a certain speed and they shut out.
Right. They sort of call that, if I'm not mistaken, I think you sent them over here, the slingshot effect. What they do an elliptical orbit, and you remember what I was saying, when an object is far from it, it slows down. When it comes close, it speeds up, and it slows down and speeds up, and when it speeds up far enough, it actually breaks away. It saves a lot of fuel if you try to just break away on your own. It's kind of like rocking a car. Not quite. You do it circularly. You rock it and do faster and faster, and then finally it's going fast enough it can actually leave the orbit. And that's what they do. And it actually, even though it takes several to go around, you're using the body's Earth's gravitational to do it for you. And when they go out to others, they'll sometimes go around Mars and do it, swing them to Jupiter, and Jupiter swing them out to Saturn. So it saves a lot of fuel. Yeah, it's pretty incredible, that people have come up with those ideas to do. So let's look. Oh yeah, I was just going to say, look at the table. How many we have tried to look at and understand, and again, here we see another country come into the picture. Japan. I hadn't seen Japan listed in the others. So you have the U.S., USSR, Japan, ESA is European Space Agency, and JAXA. I'm trying to remember. I don't even know who that is. I do not. It wasn't in the previous book. I don't know what JAXA is, the owner. Could that be a private? I don't know. It could be, maybe. I didn't know anyone was doing that. Okay, so let's look at what comets are. They're small. They're solid. They're certainly objects. A couple of models that we have of them, and they're probably pretty close to true. A good description, really descriptive, a dirty snowball model, okay? So what you have, remember they come from way out there, so way out there where nothing is gases or liquids, they're all solids because it's so cold, including water, frozen CO2. Now we have a name for that here on the surface of the Earth. When you talk about frozen CO2, what do we call that? rock concerts. Dry ice. If you're sending something, shipping something that has to stay cold, usually pack it in dry ice. Solid carbon dioxide. It's really cold. Okay? You better be wearing a lot of gloves when you deal with it. Solid ammonia. Remember, Titan had rivers of ammonia on it, or no rivers of methane. So this is solid ammonia and methane. Now that's the frozen part, okay, kind of the snowball part. The dirty part, it has lots of dust and rocky bits embedded in those frozen liquids and gases, okay? That's what sort of holds it together. Now, the head is mostly that, okay? A solid nucleus, and then there's a coma of gases that trails it. Now, I say trail it, but that's not probably the best. That's what it looks like it's doing. There's two types of tails, this coma of gas. One of these is ionized gases. Now, do you remember what an ion is? Say that again. Okay, very good. It's what an atom is it's got a nucleus and a cloud of electrons. In the nucleus are so many protons and so many neutrons. In the electrons, you have to have the same number of electrons you have protons, so it's balanced electrical. That's an atom. An ion is when you have excess electrons or loss of electrons. So in other words, it's a charged particle. Okay? And when you say electrical, that's right on the money. Either it has loss of electrons or gained electrons, but it's no longer electrically neutral. So ionized gases or dust. Okay? Now, why I hesitated saying trails it, because sometimes it actually leads it. The tail always points away from the sun. So when the comet is coming in, the head is here, the tail is out here. When it gets close to the sun, it's doing this, and when it's going out, the nucleus is here, and the tail is still pointing out, but now it's leading it, because it's not like an airplane leaving a track in the air. It's always points away from the sun. The nucleus always points toward the sun. Now here's their picture. Your book is heading the other direction, but it's really very, very similar. The nucleus is right in here somewhere. How big, I don't know, probably just right in there. This is the coma. Okay? They can be ionized gases or it could be dust. Now what we see, if they're ionized gases, they could actually be emitting light, because charged things sometimes do give off their own light, or they're just reflecting the light of the sun. That's, to me, more likely. And so that's why it's always, and that could be leading it going out. That seems bizarre. It's not that it's losing gases going out here, they're just there, and you're reflecting light off the sun. And they're in front, and this is coming up behind. It's rather bizarre. You don't know which way this is traveling. It looks like it's traveling this way, it could be traveling that way. It could be traveling sideways, as long as this is pointing toward the sun and that's pointing away from the sun. Okay. As the comet nears the sun, it grows brighter, with the tails always pointing away from the sun. Okay, nothing new there. Let's go back to this again. All that's frozen because it's so incredibly cold out there. What happens when that comes close to the sun? Some of these things start evaporating a little bit. So it loosens and leaves little dust and rocky bits behind. So everywhere a comet has been, it leaves some debris. Okay? Maybe some of this that's in the coma, maybe not, but all of it started here, and that, as it gets closer to the sun, some of that actually melts and is on the way in, and on the way out is dropping off trash. It's litter bugs, okay? It's just leaving things in this path.
I get emails from space.com.
Uh-huh.
They said like last week, the week before last, we were going through the trail of Haley's coming.
Oh, yeah, okay.
Like see meteor showers and stuff
Uh-huh.
like that. Brief from Haley's coming, which was what, 30 years ago or something.
Yeah, exactly, yeah. And actually the correct pronunciation is Halley's Comet, but everybody calls it Halley's Comet, yeah. But it's Halley's Comet, yeah. And that's not the most spectacular, but when you have the meteor showers, that's what you're doing. You're passing through the trash left over by some comet 30, 80, 150 years ago. You go through that, some more of that, and if they hit the Earth's atmosphere, then that's what you see as meteors. We're going to get to that. And that's the reason I didn't want to call these meteorites. Meteoroid is the name it should be there. We'll get to that later, so we're coming back to that. Okay. Now let's talk about asteroids. How far off are the asteroids? Are they like comets, way out there to 1 light year away? No. Asteroids come between Mars and Jupiter. They're pretty close to begin with, okay? Located in the belt between Mars and Jupiter. Now, they can get up to, some of them are as large as 1,000 kilometers. I think that's the diameter, okay, which is a pretty big chunk of rock, okay? Pretty good size. Varied composition. The innermost part of the asteroid belt are mostly stony asteroids. Now, when you see the word stony, think silicates. Okay? Silicates. Remember, the core of Jupiter was iron and silicates. That's the silicate part. The surface of the Earth, the crust of the Earth, mostly silicates. We'll cover that in a later chapter. Mostly silicates. So when you see stony, think that. Sort of like the surface of the Earth. The outer belt, all they say is dark with carbon. That doesn't really describe it well to me, except that it's just sooty. I mean, it's just carbon in it, and they're fairly dark. Others, and these could be anywhere in there, are iron and nickel. Okay? Now, when we get to the chapter on the Earth, which is, I think, the next chapter, we'll see iron and nickel go together a lot, and they are what make up the core of the Earth. Iron and nickel. More iron than nickel, but still those two hand in hand. And if you look at them in the periodic table, and I think you said your books didn't include the periodic table except in chapter 8, but if you look at the periodic table, there's iron, then cobalt, then nickel. Those three are usually associated with one another. And in the core of the Earth and in these asteroids, some of them are mostly iron and nickel. So that, to me, would indicate they were one time the core of something that got blown out. The stony parts were probably the surface of things that got blown out. The other part, dark with carbon, I don't know. So, these asteroids were formed in the original solar nebula, so therefore they're not a lot different from our core, our constitution. All the stars, planets, all the moons, they're made of the same. Now, here is the interesting part. A lot of them hypothesize that perhaps this should have been a planet in there. And if you look at the spacings, it looks like there should be a planet there, okay? Because you go from Mercury, Venus, that's a regular spacing, Earth, fairly regular, Mars, fairly regular, but then you go like 2.5 times, or 3 times, more than 3 times, before you get to Jupiter. So if you had had another planet there, the spacing would have been very even. Now, remember, now we haven't hit this yet, we're going to hit it a little bit later in this chapter. They think that when the sun was, blowing up and, radioactive and all this kind of stuff, sending stuff flying into the thing, we were sort of in a big disk, fiery disk, and the parts of the disk sort of accumulated together, and those became the planets. And when they say clumping, to me that's accumulated, that Jupiter was so close, had such a strong gravitational field, it kept that would-be planet from accumulating or clumping together to make another planet. Good theory, okay? And that may also be part of the reason Jupiter stole a bunch of moons from there too, It's just that strong. Okay. You have the sun here. Now, obviously, this is not to scale. If this were to scale, the sun would be large, huge, and you could hardly see Mars, okay? But they just scaled the sun down here. The astronomical units from the sun to Mars was about 1.5, right? Okay? To Jupiter, 5, wasn't it? I believe that's right. 5 astronomical units. So you see the others were close to doubling, and from there on out they're close to doubling. 1.5 to 5, that's more than tripling. So the 4.5 would be tripled, so it's more than tripled, coming close to 4 times. And if it was 2 times, that would put the next planet somewhere in here. The interior part of the asteroid belt is about 4/10 of the distance between the sun and Jupiter, and this is about 6/10 the difference. Right in between would be right around half. And again, the outer planets, they almost seem like they're doubling as you go out, so the inner planet would be half. That's right where another planet should be. Okay? There's not one. They think it's all Jupiter's fault. Jupiter's strong gravitational field kept that from clumping or accumulating together. Now, there probably was other things involved with it, but that's what the speculators say. Okay? Now, not a whole lot on asteroids. They all live in that belt. Not quite. Does anyone remember hearing a report, and I think it's probably been 5 to 10 years, maybe a little longer, that something hit Siberia? Really major collision there. Fortunately, Siberia is very lowly populated, so I don't think anyone lost any life or much. There was a huge crash there. Like I say, it seems like it's been 6 to 8 years ago, somewhere that way, maybe longer. Time flies when you get old, you know. Okay, so what they think that was, I would have said a meteor. They said it was actually an asteroid. So what could have happened there? Well, remember those gravitational nudges that sent comets coming in? Well, all these pieces of rock in the asteroid belt around maybe Jupiter or Mars or something gave it just enough of a nudge that one of these lost enough energy that it came out of orbit and then started heading toward the sun. Unfortunately, about that time, Earth happens to be right in front of its path, and fortunately it hit Siberia, not New York City, or London, or Moscow, or Sao Paulo, or someplace like that. Because if it had hit a large population center, massive deaths. Because that was one big crash out in Siberia. And they claimed it was an asteroid. I thought, No, that would have been a meteor, wouldn't it? And they said, no, probably an asteroid that somehow lost its orbit. Okay, so let's talk about meteors and meteorites. Does anyone know the difference between a meteor and a meteorite? Okay, very good. It's a meteorite only if it hits the Earth. Before it hit the Earth, it came into the Earth's atmosphere and was a shooting star, falling star, not a star at all. That was a meteor. But guess what? It was a piece of space junk out there before that, and that was a meteoroid. So when we're talking about the smaller particles in the solar system, they said comets, asteroids, and meteorites. They're meteoroids. The other stuff that's just out there, floating around, hasn't come to the Earth's atmosphere and become a meteor yet, and certainly hasn't hit the Earth's surface yet. They should have said meteoroids. And these are your remnants of the comets and the asteroids, okay? As those comets come in and start melting a little bit and losing and breaking up is hard to do that, okay? Then those pieces that are left over, those are those things just hanging around in our solar system. And then we or other planets cross into the path and smack them, okay? So a meteoroid becomes a meteor when it encounters the Earth's atmosphere, okay? And the meteor showers, we're talking about, we just had one from Halley's Comet, when was it, a few weeks ago you said? Yeah, okay. What happens is the Earth passes through, it says through the comet's tail, it's through where the comet's tail had been, okay? And then the meteorite is some of those meteors that start glowing when they enter the Earth's atmosphere, burning up, but don't all the way burn up and actually survive to strike the Earth's surface. That's called a meteoroid. I mean, a meteorite, okay? So meteoroid became a meteor and then made its all the way to the Earth and became a meteorite. And guess what kind you have? Iron. Remember the asteroids? You had some of them were iron. Stony. You had stony asteroids as well. So you see these are things. Now the stony ones, I have two different classifications of them. Chondrites and achondrites. Okay? What a chondrite means, it has chondrules. Okay, what does that mean? Let's see if your new edition does a little bit better. There was just one little, I think it was less than a paragraph. Yeah, here we go. Yeah, same thing. The stony meteorites, okay, are further subdivided in two groups according to their structure, the chondrites and the achondrites. Chondrites have structure of small spherical lumps of silicate minerals or glass called chondrules held together by a fine-grained cement. Achondrites do not have chondrules, okay? And that's all they say. Now, I don't know if any of you have had any experience with the mining process. And let me correct that. The steel making process. Have any of you? You have. Okay. The ash that sometimes is left over has little balls of silica. They have a name for it, and I can't think of it now. And that, to me, is what a chondrule is. Little spherical shapes that the silicates melted and then reformed with little things. That to me is what I relate that to. There's a name for it, I can't think of it now. Do we need to take a break? Okay, let's do a 5-minute or less. Oh, you got it, it's in her purse. No, I'm just kidding. Okay. Okay. All right. So let's pause here Okay, we're recording again, and we had just finished talking about meteors, meteoroids, meteors, and meteorites. Here are some of the showers, meteor showers. Now, they didn't list one for Halley, but sort of good and bad news here. We've already missed the one that went through Aquarius. That was on May 4th, but it wasn't much of a shower, okay? 5 meteorites per hour, or meteors per hour. And if you think about that, that's about one every 12 minutes. An hour will get pretty bored out there waiting very many 12-minute periods just to see maybe one meteor. So I'm probably not going to get too fired up about this. Now, too bad this is just after the term is over. But that's a pretty pleasant time of year, especially in the evening. So if you can get out there around August 12th, especially if you get somewhere that doesn't have much light pollution, I don't know what August 12th falls on, but I think we'll be off then. So if I can either be up in Smith Lake,
Saturday.
it's what?
It's Saturday.
It is a Saturday. Oh, nice. If I can be, we have a place over in Georgia that's 8 miles from the closest stoplight, so that's pretty far out. And up at Smith Lake, we have a place on Smith Lake that's further than that, I think, from the closest stoplight. So they're out there with not much light pollution. Those would be worth to go out there and watch. 40 per hour, that's about one every minute and a half, right? So that's, I think I can sit and watch that. So hopefully it'll be a clear night around August 12th. Another one around, and my favorite, I don't know Perseus. I know Perseus is out there. I never can pick it out. Orion, I can always pick it out. October 22nd, 15, that's one every 4 minutes. Not sure I'll make that. Taurus, the bull, these are the Taurid. These are the meteorite showers called Taurids. That's once on November the 1st and then again on November the 16th. What happens is we pass through where it came in and then where it went out, or vice versa. So you actually have 2 passes there in November. And the next night, Leonid through Leo. And there, the big one, unfortunately, it's in December 12th. 55 per hour, so that's almost 1 minute. So that's in the Gemini constellation. You'll see most of those. Now the book has some pretty, the first time I've seen one of these, a time-elapsed shot of one of the meteor showers. They don't say which one or how much time elapsed, but it's pretty impressive. Okay. They get. Oh, that's it.
They're good at onion rings.
Huh?
They're onion rings.
Yeah, but you can't eat it.
Yeah, I don't want them anymore.
You don't.
They're good. They're better this time.
Yeah, I really don't eat onion rings much. Wait and see if the other guy will take them. Oh, you already saw him? Okay. Well, I'll eat anything.
They produce methane
But
gas.
what's that? What?
They produce methane gas.
They probably do. Okay. But they also show 2 meteorites that have made its way to the surface. The first being a stony meteorite. Now, I think in the text, the old text, they had these 2, but the pictures weren't nearly as clear as these. And then they have an iron meteorite. And here's the thing. It says that it's been cut, polished, and etched with acid. And I think, well then, what are we supposed to see here? I mean, you've done all this to it. What did it really look like beforehand? I don't know. But both pictures were like that in the previous edition and this one, even though they're different pictures. All right. Any other questions on meteors or meteorites? So coming up, August 12th, a great night to go out and look for a meteor shower. I meant to ask y'all, and maybe especially James, because he seems to keep track of this, when is the solar eclipse? I should know this.
17th of something. Next
Is it June or July?
maybe July.
Okay. I saw it in the paper, and I thought, man, that sounds like it's soon. I was thinking it was further off than that, because I haven't heard anything, but I just saw the headline. Are you ready for it to go dark in the daytime or something like that? I thought, no, should we get ready for it? That's a ways off. But we'll get to that a little bit later. That's in the next chapter. But I just thought since we were mentioning the showers, we would go in and hit that. All right, any other questions about meteors or meteorites? Here's the pictures here, which kind of correspond to these two here. To me, the stony that they show in your text is far more of what I picture a stony than that. To me, that looks like a dark lump of coal. And I don't see why that would be stony, except that they say that glassy surface is what happens when it gets compressed coming through the atmosphere and heats up. What's that?
August 21st.
August 21st, okay. So it's a long ways off then. Look at that. August 12th, the second most frequent meteor shower, and August 21st. Hang around in August. Some good things going on there astronomically. And then this one is the iron meteorite, which I would have been more likely to think that was iron and that was the stony. But then they said it's been cut, etched, and treated with acid and stuff like this one. Show me what it looked like before, not afterwards. I don't know. But they're different rocks, but they have exactly the same captioning, I think.
I found a hunk of metal.
Right.
And you can tell it's metal.
Yeah.
It's heavy. It's got dimples all on
Mm-hmm.
it. Could that be like a meteorite?
It could, I would think. We, the farm in Georgia I talked about, down near one creek, but scattered throughout fields around there, you'll see what they call chert and just, silicate rock, scattered around. But then every now and then you'll find a dark piece that's much denser, heavier feeling, and it will sometimes have bubbles and pits and things like that. And we wondered, could that be from a meteor? And someone told us, and I haven't actually seen this, that if you look at the aerial shot of that area, from a plane picture, and look at sort of a topographical thing, it seems like there is a depression there that there could have been sometime way in the past a pretty big impact with a meteor, and that could have left these maybe remnants from that. So yeah, we've wondered about that. But then I've also heard, because we do have some marshes and swamps around, there is something called bog iron, and when I've seen and heard it described, seen pictures and heard it described, it has some of those same features. So I don't know. It could be or may not. We had on the farm when both when my mom and dad were alive, my mom had some bunion problems, and she went to see a podiatrist in Augusta at the medical college, I think it was, and he was just the nicest guy. He had been a football player at Florida State, which I don't usually picture them as going into medicine, but he was big, tall, but very nice guy, and you could picture he could have been a football player. And they really liked him and he liked them. They found out he was a hunter. And we have the farm, but none of us really hunt. So they invited him. They said, look, if you want to come hunt. So he would come out periodically and do it. And when he saw some of that, he said, I think this is from a meteor. And he sent it off someone he knew at Florida State who had a geology lab. And I remember they sent something back and they were not very keen on they said it could be, but they thought it was something else. Right now I can't remember what it was.
Was it metal or just rock?
It was ironish, Yeah. Now, I had a student in this class several years ago now, and actually I had her dad in the class several years before that. He was really interested in this kind of stuff. I think he's teaching physical science in high school somewhere now. But she brought in a smooth, glassy-like rock, but it had been fractured, and it was sort of mottled green color, just really a brilliant color. And she said her grandfather had owned a field that just had lots of that scattered all over the field, and some slightly under the surface. And there had been a big chunk, and like 4 grandkids, so someone decided to break it into 4 pieces, but break it, give a piece to each grandkid. And I still have a sliver of it she brought to me that had broken off of that at home. I never have figured out what in the world that is.
That was a reality show maybe 10 years ago. We had guys, media hunters. They would get out there and find those things that get expensive too.
Oh, I would guess so.
They slice them like, picture there. They display them like that.
Yeah.
Media hunters, if you
Yeah.
can find it.
Yeah.
It's probably on Netflix or something.
Oh, okay. I'll have to get my wife to navigate those things. I haven't bothered to learn how to do that. I'm a dinosaur. Okay, if you hadn't noticed. Okay. Now let's look at, this is 15.3, origin of the solar system. We've been talking about it all the time. Now let's go and sort of put it together. Remember what it was called before it was a star, any star? It was called a protostar. Okay? So we're going to look at the protoplanet before it was a planet nebular model. Okay? Now this isn't going back to the nebulous of gas that forms a star, but it's sort of the gases that then formed up the planets. So in the first stage, this is the formation of the heavy elements in many earlier stars and supernovas. Remember, the normal process of fusion, hydrogen to helium. And then when the hydrogen begins to blow out, there's a expansion because you have a contraction because you don't have enough fusion to push out anymore, and it fuses and gets real hot again, and now it may actually get hot enough for the helium to fuse to be carbon. And if it goes through, if it's a big enough star as it's dying and goes through a number of those, one of those, then the carbon fuses ultimately to become iron. Well, when you have so that's where a lot of the heavier elements come from, that process of repeated fusions. But on a supernova, which has an enormous, contraction and gets extraordinarily hot and then blows out, that's when you fuse to become the heavier elements beyond iron. Iron is only like 56, not halfway through the table, or maybe only 36. No, 26 actually. So about a quarter of the way through the table. So the heavier stuff gets there. So the formation of the heavy elements and many of it that were leftover remnants from many of the earlier stars or supernovas that formed the masses of gases that became our sun. Okay? Now, the concentration in one region of space as dust, well, I guess I should show the thing. Okay. This is what it's talking about there. You get when the sun is still sort of a protostar, it's heating up and blowing things out and stuff like this. You get this formation of heavy materials throughout this and in the sun too, but everything's pretty much molten and hot and messy. Well, then the concentration in one region of space as dust, gas, and chemical compounds, and that would be here. Here is going to be the sun, ultimately, or the star, whatever it is. But out here you have these other accumulations, things spinning wildly, and of course when they spin, the heavier stuff tends to go further out, The lighter stuff stays in. It sort of segregates this stuff. See, is that right? No, I'm sorry. The lighter stuff, centrifuge. Yeah, I think the heavier stuff is that. So anyway, some of that goes out here into the bands that are later going to group together and form planets. Okay, that's the stage A. Okay, stage B is then formation of the large rotating nebula. Okay, as this cools and the sun sort of settles down and becomes its own sphere, then what was out here had been flung out and shot out and, you know, spinning around out there. These things sort of group together. That's what they're earlier calling the clumping. Okay, I found that a really unusual word. Formation of large rotating nebula that are out here spinning around, and they kind of show Mercury, Venus, Earth, Mars. Relatively, they got the sizes about right, okay? And these masses of gases, they start cooling, they sort of clump together, you know, they're spinning around the sun, they're probably rotating on an axis as well, and as they cool, they sort of group together. Most of the mass concentration, obviously in the simple protostar, it's not a star yet, getting there. Remaining material forms this accretion disk, and that's what I've been talking about here and here. And in the accretion disk, you get that stuff spinning around. The material in the accretion disk begins clumping. They like that word, clumping. So the different planets or materials are clumping together. Okay? Now, remember the sun's still a protostar now, so it still could be doing, you know, eruptions or instabilities or unstable states, and so it's doing. And maybe one of those, when Mercury was just beginning to form, maybe one of those blew up or something and blew all the atmosphere away, and later the other picked up on some of that. I don't know. That's a guess. Okay? Maybe what Mercury has no moons too, and maybe Venus as well. Stage C, the proto-sun becomes a star. Okay? I would have said the proto-star becomes our sun, but they said it the other way. Solar ignition flare-up may have blown away the hydrogen and helium from the atmospheres of the inner planets, because we don't have that much in ours, even though we have a substantial atmosphere. Venus has even more atmosphere, but still not hydrogen and helium. That's all been blown out to the farther out ones, okay? The protoplanets have heated, and then as they cool slowly, they separate the heavy and the light minerals. Heavy minerals toward the center, lighter minerals toward the surface. Iron and nickel toward the center, and your silicates on the surface, okay? Now, you have some mixture all within, okay?
Is that theory same with binary stars?
Okay, now, excellent question. I don't know how binary stars do what they do. A lot of them, some of them anyway, one of them is the dying star and one of them's main sequence star. How did they get together? Maybe the dying star was the biggest one, and maybe it burned up faster. I just don't know.
Because I keep looking at Jupiter as a star, you know.
No.
Maybe, I'm just saying it's gas. Maybe when our star died out, you know, it'll feed Jupiter or something like that. You know,
yeah, but Jupiter doesn't have anywhere close enough mass to have any
that's
fusion.
What I'm saying.
Yeah.
Maybe our sun took all the mass from. Like,
Oh yeah, the process here, back in stage A, most of the gases stay in the center. That's why the sun got so stinking massive. It's just this accretion disk out here just sort of got the leftovers. They're sort of slung out there. And some of those could be heavy minerals and things like this. Then when the sun sort of settles down, there's still a protostar somewhat. These are still pretty hot gases here, but they start clumping, as they say. Now what they don't show is the next one here, and then the next one, a huge clump, and when it starts clumping, it keeps the next one, the inner one, and that would have been the asteroid belt. That's at least the theory. I don't know, you can't reproduce it, so it's always going to be a theory. So the larger bodies cool slowly, with heavy mineral materials settling over longer times into the central cores. And that's why they think it's iron, because that's the predominant heavier material. Now you have some heavier things out there too, they would be down there too, but the main byproduct of the fusion process is iron. So that's going to be the heaviest stuff on most of them, for most of the mass of it, and those are going to head into the core. So that's part of the speculation of why it's core, the iron core. And with that in mind, and then doing the gravitational and density type stuff, the model fits for iron really well. Do they know for sure? Nah. No one's drilled down in Jupiter to find out, nor will they ever, I don't think. Okay. But it's their best guess now. Okay. Ideas about the solar system. Now, this is a strange place to put this, but it's going back in history now. For much of mankind's life here on Earth, when we became intelligent enough to ask the questions, attempt of many of the early Greek astronomers and philosophers to explain the observed motions of the sun, moon, and stars. Now, we've already talked about this, right? It looks like the sun goes around us, doesn't it? It rises in the east, goes overhead in the middle of the day, sets in the west, goes gone about the same length of time, and then shows up again, back in the east again. So you picture that it's going around us, okay? That's what it would seem. The stars do the same thing. They seem to follow sort of like circular patterns around the sky. North Star sort of stays where it is. Others turn around it. Strange but true. But the moon rises in the east, sets in the west, on a different cycle, okay? Different ways than the sun does and so the stars do, okay? But they all seem to go around us, more or less. Now, the problem kids were in the neighborhood were the planets, because they sort of rise in the east and go around, but every now and then a planet will be doing this, and then it seems to turn and go back and do this, go the wrong way, and then it turns and goes back this way again. They kind of wander around and don't really follow a very good pattern at all, okay? So hang on to that thought. Many of the early Greek astronomers and philosophers, they came up with all these complicated models to try to describe why these motions happen the way they did. Here's where the problem was. They put Earth at the center of the orbits and then tried to make the orbits fit. And they could come fairly close, reasonably well, never to make everything fit. Exceptions for the model were explained by the Ptolemaic system. Ptolemy was, I always pictured him as a pharaoh type person in Egypt, but he, maybe another one had a similar name, was a pretty great scientist, or maybe it was the same person, I don't know. But he came up with this really complicated sort of way to explain this, and it did a pretty good job of explaining more than anything else, but it was so complicated. Now, completely different subject here, but I have heard so many really neat quotes from Albert Einstein. I mean, he was a brilliant man. And he had this one, there was one point in quantum mechanics and all this stuff that was happening in the early part of the 20th century. People were coming up with all these things, and the systems were just getting really complicated and confused, and They kept coming up with more particles, and actually some of them were not new particles. They just found them in a different way, and they thought they were new particles. And Einstein's summary of that was, he said, I probably have the words wrong. He said, well, God is clever, but he's not malicious, or something like that. That the system has to make. It may take a while for us to find, but it can't be this complicated. Nature is just, in some senses, fairly simple. Well, by the time they got to this, it was really complicated. Now, still there were inconsistencies in the system, even Ptolemaic system. They kept growing in number and becoming more complicated to explain. Well, then how do you do this? This didn't do this, it did that. The roots of this belief, now I think there's a little bit of a bias here, but there's a lot of truth in this statement, true. The roots of the model were not based on church belief because the early Greeks were way before the Christian church as we know it existed, okay? The Jewish faith was there, but when you say church, I think Christian church. Sure, the Christian church promoted this because everybody believed it, but they were basing it on the Greeks. So I think the roots were in the Greek, and the church just built on that. But the church was pretty adamant about it too. That's why poor old Galileo was put under house arrest. If he hadn't been such a famous scientist he was, he probably would have been executed. But they were afraid to do that because he had such a strong following. So they just put him under house arrest and basically forced him to recant his support for Copernicus' ideas. Okay? He said, yeah, I support that, and he continued writing, but wouldn't publish a thing after that until after his death, and then he directed his heir to publish this, and he was still finding things that supported Copernicus. So here came the heliocentric model. The idea that the Earth, things didn't go around the Earth, but the Earth revolved around the sun, first came up with by Copernicus. The inconsistencies in the geocentric model were now explained beautifully by the heliocentric model. Okay? And here's one of those. Okay? These aren't exactly months, but you could almost, if they were a little more evenly spaced, you could think of these as months. Almost January through October. Okay? Because we're going around the sun. Sun's in the center, we don't show it. You look over here and see Mars. Now Mars is traveling around, but it's a lot bigger orbit, and therefore it takes a lot longer. And say January, you look up and see Mars here, and he's there in the sky, normal, fine. In February, he's moved over to there. Okay, good. March, he's moved over to here. Of course, we're moving, he's moving, but not at the same rate. So yeah, everything looks like he's going a pretty good path here. Until you get to April. Now this isn't really as much, but let's just imagine that. And suddenly he looks like he's sped up some. Okay? Then in May, you look up there, and he's going backwards. He had been traveling this way across the sky. Now he's traveling that way. And then in June, it's even further. In July, he's turned again. Okay? Made a big U-turn and come back again. And then from then on, July, August, September, October, he's back on a regular path. What happened? Did he get drunk? No, I didn't say that. I mean, he's just sort of lost his way there for a while. Well, what it is, on a geocentric model, almost impossible to explain. How he can travel back? No. Okay. It's just almost impossible. And that's why they're called planets. Planets mean wanderer. They lose their way, Well, when you do the heliocentric model, plot them out, he's traveling along in a very regular plane. We're traveling along in a very, it's just our perspective of him is a little wacky because we're going at different speeds. And he's way further out. So this shows how the heliocentric model explains some things that Ptolemy and all of the others couldn't come close to explaining. and they just got more and more complicated and still were able to. Okay? So the inconsistencies were explained. Then along came Kepler, Johannes Kepler, and he came up with laws that would further explain the heliocentric model. Because I bet you Copernicus and the early helioscopes always figured that these were circular orbits. That made sense, right? Sun at the center and we're going around it. And we know Kepler came up with the fact, hey, they're not really perfect circles. They're ellipses. Now an ellipse is a lot like a circle, except it has two foci. Circle just has one. An ellipse has two. The sun's at one, nothing's at the other. So when you're out here, you're moving a little more slowly. When you get a little closer, you are going faster. And he came up with 3 sets of laws that explain everything about our orbits. Boy, he was tedious in his analyzing data. I mean, it was just incredible. And all he could do was say what the measurements were. I mean, he measured, took angles, took all this kind of stuff, and came up with a mathematical model, these laws that explained everything. But he couldn't answer the question why. Until Isaac Newton came along, and that's where his principles of motion, but also he had to do instantaneous velocities and accelerations and things. He had to invent an entirely new piece of mathematics, calculus, to explain the math that would explain Kepler's laws. Kepler observed it, but it was empirical. He couldn't say how this happened, why it happened, and that's what Newton was able to do. Pretty incredible history. Whoa! That is the last slide in the text. Okay? I hadn't been turning my pages well. There's a pretty good descriptor there of Venus as both the morning and evening star, so I think that's probably worth a look. Actually 2, A and B there on 1523. And then we saw the Mars one. And then the figures you see on page 1525 and 26, they describe 2 of Kepler's laws. They exaggerate it like crazy. No planet out there has this elliptical of an orbit. They're all much closer to circular, but they still are slightly elliptical. And but you see the first 2 of Kepler's laws described. They give a mathematical formula for the 3rd law, and it is pretty incredible itself. Okay? Now, figure, I wish I had this on a slide, figure 1527 is describing a lot of what we were talking about. If you plot, now this is not on a regular scale, it's the period, that's how long it takes for the given planet to go around the sun, and the distance from the sun in astronomical units here. And this is on a log scale. Yeah, both of these are on log scales. That means they're exponentials down here, and you do have that down here. If you plot this, look at that. Mercury, Venus, Earth, Mars. Skip a space, Jupiter, Saturn, Uranus, Neptune. Look how really close to evenly spaced those are if you just had one more planet in there where the asteroid belt was. It's a pretty telling picture here that really suggests, yeah, there should be another planet there. And whereas before, when we were doubling, every time we went out with another planet, a log scale brings it in and makes that linear. So that's what makes them so evenly spaced here. Okay, and that basically is, in a sense, explaining Kepler's third law. There is an example here. By applying the concepts of planetary motion discussed in Chapter 2, which we didn't do, so therefore we're probably not going to go any further than that. That's where those formulas come from, and you can do some work with it. Again, it's way, assuming you know stuff that in the front half of the book that we don't. Let's look at 15.6. What is the mass of the sun in kilograms based on the orbital speeds and distance from Jupiter? And there you get an answer. And that's one way they came up with the masses of the sun and other things. No one can put them on a scale, but you measure the effect of their gravitational field. Now, people behind the news, the person listed here, Gerard Peter Kuiper, I think is how you pronounce that. He was born in the Netherlands, the Dutch born, but he became a U.S. astronomer, born in the Netherlands. After completing his education in the Netherlands, he immigrated to the U.S. and 4 years later became a naturalized U.S. citizen. And you can read on there. If you want to write on Kuiper, this can't be your source. Okay? You need to go outside the book to get your source. Okay? So, do so. Yeah. Yeah, whatever your format you're using, I'm sure they all require you to list references. Now, you can get by with just one for me. Most research papers are going to require more, and usually it's better to have more, but I'll let you get by with just one. So that'll be fine. All right, I'm going to be the broken record again. Nothing replaces reading the text. Okay? Trying to keep up with time. So, please, if you haven't already, go back and read the book. It's a good book. It's got a lot more stuff in it. I mean, the text is almost the same as you have in the previous edition, but the pictures and the descriptions, I think, are even better in this one. But then once you've read it, the summary is exactly that. It just summarizes some of the high points. Especially what I look for here are the italicized words, or if anything you may find bold. Of course, names and stuff are pretty important as well. Then you have key terms listed. Now, unfortunately, they list them alphabetically, but they put the page number where they first appear, so you don't have to go around looking for them. And then applying the concepts. In this chapter, 41 questions, multiple choice questions. I think that's a few fewer than normal, but they give all the answers. So to me, that's the best way to study for the test. Go through these, jot down what you think the answers are, compare them with the real answers. Those you get right, don't worry about them. Those you get wrong, go back and see if you can figure out why you got it wrong. If you can't figure that out, if you're convinced you got the right answer, bring them to class, and we'll talk about it. Those will be the best places to launch into the discussion. Then questions for thought, pretty good number there, 19. I think that's probably a little higher than normal. For further analysis, 6. That may be slightly more than normal. Sorry. Then there's a little invitation to inquiry about how long is the conversation. There was pretty close to something already done like that in the text, but you can look again. For those of you who do have a book, which I think most of you do now, the Group A parallel exercises have the answers in the back. Group B do not. So you could do any of Group A if you want to, but again, a lot of them are based on stuff in the first half of the book which we didn't cover. So if you run into that wall, don't bang your head against it. Just don't worry about it. Okay? You won't be asked to do the complicated calculations that require all that stuff from the earlier chapters. Most of what, if I ever ask you to do some calculations, there will be some that we've done very similar to things in class. Okay. That finishes chapter 15. Any questions on 15? What's that? Yes, the test will be Tuesday. Today's Thursday, right? Oh, yeah, that's right. It won't be Tuesday. Yeah, the test will be the last 30 minutes on Thursday. Now, here is the next question. We have approximately 45 minutes left. We have one or two options that I can think of. Okay, you could probably think of more, which I wouldn't go on with. Okay, but the two options I would come into, I can start chapter 16 and get as far as we can go. Okay, and then what we would do next time is only do, let's see, we're here for close to 3.5 hours. Half hour is going to be the test. 2 hours before that would be the lab. So an hour before that. We just do 1 hour of class on continuing chapter 16. Then at 1 o'clock, start the lab. If we finish the lab before 3, then fine, we'll go on and have the test. If it don't finish the lab by 3, we'll stop the lab and give you the test at 3, and hopefully you can finish that by 3:30 when you're through go. Okay, that's one option. The other option would be starting the lab now. Okay, and then we're not going to finish the lab now, but we can start it now. And then when we come in on next Thursday, we'll continue the lab until we finish the lab. Then we'll go back, start chapter 16, because that way we wouldn't have started 16. Start chapter 16, go as much as we can until we get to 3 o'clock, and then have the test on 15. So, second? Okay.
I like the second option.
The second option, to start the lab now? Start the lab now and continue it on next Thursday? Okay. Is that okay? Huh? Same thing. Okay. All right. But either way, the test will be the last 30 minutes. Okay. Now I took her to the lab, but she didn't have it run off when I was last there. So I need to, what I'm going to do is pause this. Not recorded, sorry. But I'm guessing y'all are the ones that are going to be here anyway. I don't have any confidence the other students are going to show up, but I got to wait until they take them off my roll. I don't guess I've got to, but I've just been stung too many times in the past by assuming they're not coming and then having someone show up. Okay. So here we have basically what we've got is, let me get my pen adjusted. Okay, what we've got here is how long does it take the sun to get back to crossing our meridian if we've moved 1 more degree, or if it's moved 1 more degree, or has 1 more degree to go. So we have a ratio. Does that work pretty well? Okay. And it's very similar to what we've done before. How many degrees is it around the sun? 360 degrees, right? And that takes, now I'm talking about our spin. Okay, so the sun seems to move that, but we spin we turn 360 degrees in how many hours? 24 hours, okay? So 360 degrees corresponds to 24 hours, time-wise, okay? Now, we want to know how much 1 degree is, because that's how far it's off every day, right? So we can either put an X down here, or there's a couple ways we can do it, okay? Anyone know how to solve that proportion? Cross multiply? Is that okay? That says 360x is equal to 24 hours. Well, we will leave off just 24. We'll leave off the units for now. So how do we solve for x? Second, divide both sides by 360. Now, I may not do that exactly, 360, okay? If I want to simplify that a little bit, that would be x is equal to, that would be how many hours, right? Let's just leave it like this. 24 hours over 360 degrees. But I don't want it in hours. I want it in minutes. So let's do a conversion here, a double line conversion. We're going to put minutes and hours over the unit bar. And which unit will go where? Minutes and hours. What goes where? So you can clear out hours and have minutes. This is how you do a conversion. Converting from hours to minutes. One's got to go on top, one goes on the bottom. What minute goes where? I always say, put the units in their place.
Hours would go on top.
No, if hours on top, you have hours squared per degree per minute. That's not going to work. Put hours down here, they cancel out. Right? So, because you're multiplying. So let's put hours here and minutes here. Okay? That'll cancel out our hours. But before we do that, how many minutes in an hour or how many hours in a minute? Y'all know that.
What was the question?
Second?
60.
60 minutes in 1 hour. Match the numbers with the units. Okay? Now, here comes the magic. Let's cancel out the zeros there. You're dividing, you're multiplying, so you can do that. 6 will go into 36 6 times. 6 will go into 24. 6 will go into 24. 6 will go into 24. 4. And that would be minutes. And if you wanted to put it per degree. So every degree is 4 minutes. Okay? So if the sun moves 360 degrees around in 365 days, moves about a degree per day along the ecliptic. If it's 1 degree east of the vernal equinox, 1 day later, calculate how long it would be to wait for the situation to be. You have to be 4 minutes later. Okay? Express your answer in minutes. That's what the last part was. This would have given you some decimal number. We converted that to minutes for each degree. Okay? We have just described one way of showing that the solar day is a little bit longer than the sidereal day. Solar day, 4 minutes, about 4 minutes longer than the sidereal day. Okay? Sidereal day is 1 spin. Solar day is 1 spin plus that little bit you make up for that extra degree you travel around the sun. Because it's noon to noon. Now, question 2 at the bottom of page 371 looks like it needs an answer, right? Figure 48.3, and there you can turn over and see it, yeah. Depicts the sun's apparent motion along the ecliptic, where the zodiacal constellations are found in a heliocentric perspective as the Earth orbits the sun the line of sight of the sun toward the background stars also moves. For example, the diagram shows the sun in Leo. If we're here on Earth, we look across the sun, it's where Leo should have been. Can't see Leo because the sun's in the way. A month later, the Earth will have moved so that Virgo lies behind the Sun. So we come a month later, Virgo is behind the Sun. Can anyone find a question in that? No, okay. They set you up perfectly, but never ask a question, and I don't have a clue what they were gunning at, okay? So we don't do anything with that. 2 is a blank. Okay? Now, 372 shows the thing we were talking about earlier. The B part of 48.2 shows how one's sidereal day later we're at point B, but we have to go just a little bit further and spin just a little bit more to get us to C. Now, obviously, that's not to scale, but that's showing the same thing we were doing. There is a great picture of your constellations and your zodiac and all that kind of stuff. And basically, these do appear on the on the ecliptic. And you'll always find these, if you can find these constellations, you can find the ecliptic. That's where the ecliptic is, because they're always on. The trouble is, I never can find these constellations. They're a mystery to me, okay? When you connect the dots, that does look a little like a line, so I can see that. But you see, when I'm looking at the night sky out there, I don't see any connected dots. I mean, I don't see any lines or lions, either one. Virgo, I don't know what that's supposed to be, but sure doesn't show me very much. Libra, I don't even remember what that is supposed to be. Is that a balance or something? That doesn't say. Now, Scorpion, yeah, that looks like a scorpion once you have the lines in there. But without the lines, it's just a bunch of stars, okay? Sagittarius, I think that's an archer. It kind of looks like that if you have that. So I think that's what Sagittarius is. I should know that. I think that's what I am, but I'm not sure. Capricorn, that's supposed to be the horn of plenty. And I sure don't know what that is. I can't see that in the stars. Aquarius is something to do with a water creature. And that doesn't even look like a water bug to me, so I don't know what it's supposed to be. Pisces is supposed to be a fish. And for the life of me, that doesn't look very fishy. I don't know. Unless it's the tail of a really big fish and just have it connected, so I don't know. Aries, I don't remember what it's supposed to be, but that sure doesn't look like anything much to me. Taurus is supposed to be a bull. And if these are 2 really long horns up here, I guess that could be a bull. He has really short legs, though. That's the thing. I don't know. Now, Gemini, once you connect the dots there, it looks like they could be twins. Okay? Fraternal twins, obviously not identical. Cancer, how do those 4 stars make anything? I don't know. So we're back to Leo. So to me, that's just as mysterious as the what do you call that?
Cancer's crab.
What's that?
Cancer's crab.
Oh, the crab. That may be it. So yeah, maybe that even looks a little like a crab. Beats me that. I don't think I want to eat that crab. So anyway, it's just as confusing to me as the whole idea of the zodiac is anyway. So anyway, let's go.
Quick note.
Yeah.
You got an app that'll help you find all the constellations.
Right.
Star Map.
Got it. And
Sky Map.
yeah, if I knew how to use my phone, it would be great.
Yeah, but it'll show you position of the sun at night and everything.
And where to look.
Yeah.
And sort of pointed out some of the major
down
stars.
there, you just put your phone down there, you see the sun.
Oh, really?
Or you'll see the moon. If the moon is out, you can move it up and you'll see the moon on that.
Oh, wow.
I mean, it's pretty neat.
Wow, it's really impressive that it'll do all that.
If my battery wouldn't go, I would show you how it works.
Okay.
I'll show you later.
Okay. All right. So the main part of today's lab, and next week's lab too, is going to be this: the analemma. Okay. That's the tails of the sun's motion. Now remember a couple of things about the Earth. We don't move in a circle around the sun. We move in a slightly elliptical orbit. So sometimes we're a little bit closer to the sun, and sometimes we're a little further away. Sometimes we're moving faster, and sometimes we're moving slower. So that's one problem. The other thing is, the Earth is tilted at 23.5 degrees. So things don't always line up well that way. Okay? So that's what keeps the sun from being a perfect clock. And in the old days, remember, that's how before they had watches or anything close to that, and before the sand through an hourglass, which was a pretty good clock, kind of, what they used was what? A sundial. And the shadow of the sun approximately pointed to the hours of the daylight hours. Of course, at night never worked, okay? Because there was no shadow then. Couldn't count on the moon. And it would be wrong anyway. So another name for a sundial is an analemma. That's the Latin word for sundial. Okay? Now, the analemma we're going to be studying is a very different one from the one that made a shadow. The analemma is a closed curve resembling a flat-bottomed figure 8. Okay? Sometimes on some globes, not the globe I have, they'll have the analemma somewhere out in the Pacific Ocean, so you can sort of pick up on it a little bit. Okay? Now, we could, if y'all wanted to make this class a full-year class, which I'm sure you do, we could draw an analemma on the floor here. No, we don't. Facing the right way. No, we have to. Okay. If we came in at our real noon, not the time noon, but real noon every day, when the sun was crossing our meridian, okay, and we blacked out the windows, turned off the lights, and just had one little hole, say in black plastic or something, in the window, maybe have to cut down the trees, probably would, if we get away with this. But if we were to do all that, and then at noon every day, mark the spot on the floor where the sun came through that hole. At noon every day of the year. Mark that. On the floor, we would have something that looked like that. That's what we're calling the analemma. It is another kind of a sundial. Okay? Now notice there. Yes?
What do they do with rain?
Yeah, we would have to skip that. Yeah, exactly. But we can get the general shape. Okay? Now, this analemma shows several things. One is the declination of the sun. Remember what that was? How far north or south the sun was at every day of the year. Remember we did that on our star chart. And what days were it right did the sun cross the celestial equator? The eclipse across the celestial equator? 21st of March, and if you look here, find March over here, and there's 15, 20, the next one is 21, that's right where the sun crosses the celestial equator that day. Guess what other day that would have been?
September.
The what?
Oh, but when they March 21st,
That's the vernal equinox. What's in the other? Autumn. In autumn. when the sun is sitting right on the celestial equator. Okay? What day is the sun highest in the sky? Above the celestial equator? June 21st. Look at it. There's June 21st. Okay? When is it the lowest in the sky? December 21st. Right there it is. Now they call it a flat bottom figure 8. There's not a lot of change there. Those all days look fairly close, but December 21st is probably the closest. Okay? There is our analemma. Okay? You can see the tilt of the earth that moves us up and down, declination of the sun, the time in minutes. This is whether you're before, let's see, I think it's over here, before clock noon or after clock noon. Down here you have minutes of arc. Up here you have minutes of time. So, and then you have the days of the year on the circle. So you got a lot of information in that one chart. Okay? Now, I think we've hit everything here. So let's turn to page 376. The first full paragraph there, it says, in summary, the analemma graphs the sun's declination, that's on the vertical scale, the daily difference between clock noon and noon by the sun on the meridian, for every day of the year, that's the upper scale. Yes?
I stopped at 374.
What's that?
Only have 374.
You what?
Only have up to page 374.
Really? You don't have 376? You can have this one. I don't have that. The copy machine messed up. I didn't see any spare pages anywhere. Did anyone else run into that? Okay, one of those people who's not here can get that out. Okay. 376. There we go. All right. Looking at figure 4.3, we see that the sun is west of the mean sun, that is ahead of clock noon. So when you're on this side, you're ahead of clock noon. On the right-hand side, you're behind clock noon. So ahead, behind. Briefly describe, this is question 3, briefly describe the effect of the shape of the analemma if the ecliptic equator angle were to increase. So we would be 23 and a half, but maybe 24, 25. How would that affect the shape of this? Where do you see? There again?
Well, then we get bigger, right?
Okay, it would get longer, because then rather than stopping at 23 and a half here and 23 and a half here, it would have to go to 24, 25 or something. So it would stretch it top to bottom. So that's how you can answer that. Does that make sense? Stretch the thing top to bottom. Okay. Number 4, just ask you to give you information. I've given it to you before, but I'll give it to you again. It says our exact, well, we need exact, we really don't, and it isn't even exact, but it's pretty close. Obtain from your instructor the latitude of your location and fill it in below. And we're just assuming we're in Bessemer. We go across here, and we read that to be 33 degrees, 23 minutes, 45 seconds. close enough to go. Okay. That's our latitude of where we are right now. All right. Well, this sounds like the last lab. Determine the altitude over the southern horizon of the intersection of the celestial equator and the local celestial meridian. Okay? Okay? Now, basically, we're going back to this. Here we are on the globe. We're standing here. Nice warm weather, so we're standing there. Here's our horizon. There's the celestial sphere. We are at, and by the way, from the center through us, through the top, what is that called? Our zenith. Okay? And we are at 33 degrees, 23 minutes, 45 seconds from our equator. That's how far we are north of the equator. That means what it would be right here. That's the celestial equator, right? And that would also be 33 degrees, 23 minutes, 45 seconds. Because that's how far we are north of the Earth's equator. That's how far our zenith is north of the celestial equator. Okay? So what is the question asking? Determine the altitude over the southern horizon. Here's the north, here's the south. So what's the altitude above our southern horizon of the intersection of the celestial equator with our local celestial meridian? This is our local meridian. If you face due north, go through our zenith to due south, that line there is our meridian. This is where the celestial equator crosses it. The question is, what is this altitude? How do we get it? Subtract it from 90 degrees. Only I'm not going to use 90 degrees. If you remember, I use 89 degrees. And I would use 60 minutes, but I don't want to use 60. I want to only use 59 minutes and then 60 seconds. Now, why did I do that? I'm lazy. I want to make the subtraction easier to do. Okay? So, this 60 seconds would make one more minute. That would make it 60 minutes. 60 minutes would be 1 degree. That would make it 90. So, yeah, that's the same value. It's written out like this. And then I subtract from that, and this is what makes the subtraction so easy, 33 degrees, 23 minutes, 45 seconds. And what would that give us? 56 degrees, 36 minutes, 15 seconds. Yep. There is the answer you write under that determinant. Okay? Now, use the analemma in figure 48.4. Go back one page. There it is. Okay? And your answer in step 4 that we just filled in to fill in table 48. 1. Now, whoever made this up made it 47.1. I wrote 48 over it, so that's what that scribble is. The latitude, and we'll do Altgard, Norway next. Okay? We're first going to do it at our location. But the first thing it asks for is declination of the sun. What does declination of the sun mean? How high it is above what? The celestial equator, exactly. So the declination of the sun on February the 15th. First thing we do is find February 15th. You find it? Declination of the sun is measured on that vertical scale to the left. So has anyone found that yet?
13 degrees.
It looks like 13 degrees, but 13 degrees what? South of the celestial equator, right? You see the celestial equator? 13 degrees south of that. Below that, see south at the bottom, north at the top? So 13 degrees south of the celestial equator. So that's what we fill in on that first blank in that. Declination of the sun, and you can either use a minus sign to represent south or 13 degrees south. Put an S by it. That would be fine too. And that's south of the celestial equator. Okay? Now, it's also asking for the noon altitude of the sun at our location. Okay? Now, on 15 February, the sun is 13 degrees. I'm going to try to draw that. Here's the sun on 15 February, and we're saying this is 13 degrees south of the celestial equator, right? That's what the declination is. That's where the sun is on that day. Okay? So what is going to be the altitude of the sun on that day? Yeah, subtract this 13 from there. You see it's 13 degrees south of this angle here. So altitude of the sun would be this angle here, which would be 13 less than that. So what would that be? $43 degrees, 36 minutes, 15 seconds. It's pretty precise, isn't it? Okay? So that goes in the middle column by 15 February. They say February 15th. Let's go to June the 21st. What is declination of the sun on June 21st? $23.5 degrees. You should have known that without looking, right? You knew 220. Okay, that's a trick question. But yeah, that tells you that though. So, but that's where? North or south? North. So that's above the celestial equator. That's 23.5 degrees above. So I'm guessing that's about 23 degrees, 30 minutes north of the celestial equator. So what's the altitude of the sun there? Here's the sun again, but this one's on 21 June. Okay? You take your celestial equator, which is at 56 degrees, 36 minutes, 15 seconds, and now add to that, because you're above that, you're adding to that 23 degrees, 30 minutes. Okay? And what does that give you? This time let's start at the right-hand side like we should have been doing. 15 seconds, that just brings down. When you add 30 to 36, what do you get? 66. 66 minutes, though, is more than 1 hour. So that 6 minutes carry 1 hour, right? And then add that. What do you get? 80. 80 degrees, 6 minutes, 15 seconds. So that's what goes there. Now that's where we live. So that means on June 21st, which is coming up in just a couple of weeks, the sun's going to be 80 degrees up there. At noon, it's going to be real close to directly overhead, but not quite. What latitude would you have to be at to get it directly overhead on June 21st? 23.5 degrees. That's on what line? Not on the equator. The equator would be directly overhead on vernal equinox and autumnal equinox. But Say again? What's that circle that goes around 23.5 degrees above the equator? No, the ecliptic goes this way. It's the Tropic of Cancer. The Tropic of Capricorn is 23.5 degrees below. Okay. All right. Do we have time to finish the table? Or not, at least this part. October 15th. Y'all need to go. If you do, it is awfully close to 3:30. You want to just pick up and go from there? Okay, y'all have to remind me where we ended, because I don't have it marked on here or in the book. So we'll start with the lab, and we've made good progress. We're not quite halfway through the lab, but we're pretty close to it. So I think we'll finish the lab up probably within the first hour or so of class on Thursday, a week from today. And then we will do, then we'll pick up in chapter 16 and go till 3. So from 12 to 1, well, whatever time we finish the lab, then we'll pick up from there and start in chapter 16 and go until 3 o'clock. At 3 o'clock, we'll stop and have the test on chapter 15. Now, I may have forgotten to tell you last time, but I'll tell you this time. Be sure, if you want to, do a formula and equation sheet for anything you want to write down out of chapter 15. Okay? So, you can have that with you during the test. Good deal. Any questions? All right. Usually I would say have a good weekend. Now I say have a good week. Okay? I'll see you next Thursday. Sorry about that. So you hung with us the whole time, huh?
Yeah.
Good. Are you going to that adult education thing? Is that what you're doing?
That's what it is?
That's what Mr.
That's why it's in the gym?
It's an event with Mr. Hollins. Is he part of it? Yeah, okay. He said he was going to be doing something with the adult education. Okay.
Yeah, that's what I'm going in.
All right. Good deal. Thanks.